for example number 3, it says a graph is bipartite if and only if it contains no cycles of odd length. So this is a generalization of problem number 1. Number 1, it says no triangle, but here it says no odd cycle. So any cycle of odd length 3, 5, 7, then if the graph has this cycle, then it is not bipartite. The theorem is if and only if. So we have to prove it in two directions. The first direction, which is from left to right, it says if G is bipartite, then G contains no odd cycle. We will prove this problem or this part by contradiction. So proof by contradiction. And the idea for the proof by contradiction is that you assume the hypothesis and the negation of the conclusion are true. So let us write the statement. Suppose G is bipartite and has odd cycle, because the conclusion say that and has odd cycle. Assume we have one is sufficient, okay, for the proof. Let C, which is equal to V1, comes next V2, comes next V3, and goes to Vn minus 1, adjacent to Vn, and Vn is adjacent to 1 because this is a cycle. B, an odd cycle where n is odd, because we have odd cycle. Since G is bipartite, so we expect that we have two partition of the sets. So we will say also let V1, which is the first set, is equal to Vi such that I is even, and V2 equal Vi such that I is odd. So since it is bipartite, because see, we assumed from the beginning that suppose G is bipartite. Since G is bipartite, so we have two partitions. Now, what are these two partitions? The first partition, we will put all vertices that have subscript even. So what will be the members of V1? It will be V2, V4, and etc. And what will be the members of V2? Will be V1, V3, V5, and etc. And don't forget that we have also Vn inside V2 because n is odd. So it says let V1 and V2 be the partitions formed in the graph. But here we will have a contradiction. But notice that V1 and also Vn both belongs to V2. Why? Both belongs to V2 because C1 is odd, so it belongs to V2. And also n is odd, so it belongs to V2. But V1 and V2 are adjacent. And since they are adjacent and are adjacent, which is a contradiction. Now, contradiction to what? So it is a contradiction. And here I will put between a bracket that G is bipartite. And remember, for bipartite, no two vertices in the same set are adjacent, and this will complete our proof. Now for the other part, which is part number B, we will say here if G contains no odd cycle, then G is bipartite. Okay. Again, we will prove this by contradiction. So proof by contradiction. Let us write the contradiction statement. Suppose G contains no odd cycles and G is not bipartite. So here we assume for the contradiction statement is that G contains no odd cycle and at the same time G is not bipartite. How we are going to prove this part? So in my proof, I need to define a distance, and by the way, this way is not the only way to prove it. There are plenty of ways to prove this problem, and if you would like to see, just browse over the internet, write on Google the problem, and then you will see that there are many people try to prove it in a different way. But the way I'm going to prove it is by first defining a distance between two vertices. So we will say let d x comma y be the shortest distance between vertex x and vertex y. What do we mean by the shortest distance? I will demonstrate for you and by an example what does this distance mean. Imagine we have the following graph. If this is x and we have another vertex here and we have this is y, and suppose here we have also another vertex, and this is the situation we are going to have. So what will be the distance from x to y? This is not v, this is supposed to be x. I can go from x to y from different route or from different through different places. I can go from x to y using these two edges, this one and this one, so the distance is 2. Or I can go from x to this vertex and this vertex. So if you count the edges, 1, 2, 3 and 4. Or I can go from x to y through these edges. So we will have 1, 2, 3, 4 and 5. So we have 3 distances. We have 2, we have 1, 2, 3, 4, and we have 5. So the shortest is 2. So we say that the distance between x and y is equal to 2. So we need to take the shortest one. So this is the meaning of the shortest distance between vertex x and y. Now, let a vertex v be a vertex of G. And also let x, capital letter, be the set of all vertices at even distance from V, and y be the set of all vertices at odd distance from also V. So here you just pick a vertex in the graph and try to find the distance from this vertex to all other vertices. Find the shortest distance. And those with even distance, put them in a set that is called X. And for those with odd distance, put them in a set that is called Y. We can imagine this situation by the following. I will draw it just for you to understand and have an idea what we mean by X and Y and V. Suppose now this is the set for X and this is the set for Y. And where is V? Suppose V is here. So if the distance from V to X is even, you put X here. If the distance between V and W is odd, then you put W here. So this is the situation that we have for our problem. Since now I will go down and we will continue. Since G is not bipartite. And from where did we get this information? If you go back to the beginning of the contradiction statement, it says suppose G contains no odd cycle and G is not bipartite. See, it says that G is not bipartite. So according to this, since G is not bipartite, then there are adjacent vertices, and we will give them a label. Let us give them a label U and W, either in X or in Y, such that the distance from V to U and the distance from V to W have the same parity. Now when we say parity, it means odd and even. Let me visualize this situation from our diagram. Here it says, since G is not bipartite, then there are two adjacent vertices U and W, either in X or Y. Because we have two partitions, so we expect that U and W either they are here or they are here. And such that the distance, if U is here and W is here, so the distance between V and W and V and U should be the same parity. It means either both are odd or both are even. Let us assume that the distance is even. So I will put here, okay, in green color. So here I will put U, and here we will put W. So here we have U, and here we have W. Now the distance from here up to here is the same parity with the distance from V to W. Here when I say distance, and see I'm not putting a straight line, I assume that you are going to visit some other vertices to reach W, and since it is bipartite, we assume that these are adjacent. Okay, and here what does it say? Since it is not bipartite, there are adjacent vertices U and W, so this is U and W and they are adjacent, so there is an edge between them, and the distance from V to U is the same distance from V to W. Otherwise, we will not put them in one set. Now, where we will find the contradiction? Then, there is a cycle from V to U to W and then come back to V. Where is this cycle? See, here we have a cycle it says you are going from V to U, and from U to W, and from W you go back to V. So this is a cycle. So then there is a cycle from V to U to W to V back again. And what is the distance of distance or of length of distance? Or maybe we should say length, because the definition for distance is the same as length. So I will say of length. Of length. Now let us see the length. Now the distance from V to U, so we need to add the distance from V to U. And where is this distance? So you need to add this distance plus 1 as one edge added with this distance. So we are going to add plus 1 plus the distance from W to V. But this distance is odd. And this is a contradiction. Why a contradiction? It is a contradiction, and I will write between bracket that G has no odd cycle. And how come it is odd? Okay. Now, the distance here, remember that, maybe I should write a note here, that here all vertices, here, all vertices with even distance from V. And here we have all vertices with odd distance from V also. So the distance from V to U is even, and maybe I should write a small here. This is even, and also the distance here is even. Okay, so if the distance from V to U is even and the distance from VW is even, so even plus even is even, and you add 1, so even plus 1, which is odd, so we have an odd cycle. So this is why we wrote here which is odd, and this is a contradiction that G has no odd cycle, and this will complete the proof. That's all for today. Good luck, and see you in the next lecture.